Here's a kind of question that I would almost guarantee you'll find in the multiple choice section of the AP test. Rank the following from largest radius to smallest radius. You're going to have a periodic table for both multiple choice and free response sections on the AP test. So I would start by locating these elements. Now here's kind of a partial periodic table that's given in the textbook. So for example, copper's not listed on this visual, but that's okay. We can kind of throw copper in. Copper would be in the first row of the transition metal group. So I don't know, someplace between calcium and gallium. We'll just throw in copper. Somewhere in there. Now I do like this visual because it kind of shows that in general the atoms get bigger going down a group, mainly because there's more energy levels, larger orbitals, and that shielding effect is causing a weak attraction between the nucleus and the outer valence electrons. In general, going across, the atoms get smaller because there's a greater nuclear charge. And the more protons in the nucleus creates a greater attractive force on the electrons. The greater attraction, the smaller the atom becomes. Okay, so we didn't have copper in this chart, but we'll just kind of throw them in there. Rubidium. Yep, we got rubidium. Germanium. There he is. Fluorine. And carbon. Okay. So one thing that I would make note of, when you're trying to rank things like, radius or any of the other trends, I would know the extremes. People often think that hydrogen is the smallest atom, and I hate when they use the term smallest atom. Well, yeah, a hydrogen has the smallest mass, but the smallest radius actually belongs to helium. Yeah, they're both just filling the first energy level, the 1s orbital, with 1 or 2 electrons. But if you've got 2 protons in the nucleus, like helium does, that's going to provide a greater attraction for helium's electrons. So helium actually has the smallest radius. So be careful if you're ever using the term smallest atom. Well, what do you mean? Do you mean smallest atom by mass or smallest atom by radius? Now, and the other spectrum, now they technically don't even list our boy francium, but let's just put like a ghost francium in here. Down at the bottom, francium. He would have the largest radius. Francium, of the elements discovered at this point in the game, has electrons distributed amongst 7 energy levels, but then as you go across, there's going to be more protons in the nucleus. So going across that 7th row of the periodic table, the atoms are going to get smaller. So know the extremes. Francium is the big boy, and helium is the smallest. So now as you locate these atoms and you have to rank them, we're going from largest to smallest. You want to go closest to francium, all the way up kitty corner to closest to helium. Oh, well now this isn't so bad. So the largest is going to be our friend rubidium. Rubidium's the largest. Next in line, I've got to compare copper and germanium. They're both going to have electrons filling similar energy levels, but as I go across, germanium has more protons. So germanium's going to have a greater nuclear charge, meaning more attraction, smaller atom. So we're going to go rubidium to copper to germanium. Now here, this is good too. 1, 2. Germanium and carbon are in the same group, but this one everybody always gets right. Germanium has electrons distributed amongst more energy levels. So So germanium is larger than carbon. And then I would go across to fluorine. Fluorine's going to be the smallest. Between carbon and fluorine, again, we're both filling the second energy level, but fluorine's going to have more protons, meaning a greater nuclear charge, more attraction, smaller atom. I like that. So know the extremes, helium and francium, locate your atoms, and they're not going to give you anything that's ambiguous because there are some elements that have very similar radii. They're not going to do that to you. The ones that they give you will follow a very distinct trend. Now we could do this with atoms or we could do this with ions. So the second set gives me a bunch of ions to locate. So for example, potassium +1 is its most common charge. Calcium +2. Then I've got chlorine -1, most common charge. Notice there are no transition metals in this group. Then cesium and gallium. I gotta find cesium, he's hiding way down there. And gallium. There's cesium. And gallium. Cool. Okay, so now if they give you ions, a couple things that you have to be careful of. Just check, number one, are all of these ions, like, their most common charge? And in this case, yes. Then we can rank them with the same logic that we would use to rank their atoms, like the atomic radius. So I'm going to start with the biggest, cesium. Cesium is larger than potassium. They're in the same group. So going down, there's more energy levels. As I go across, atoms get smaller. There's a greater nuclear charge. So next would come calcium and gallium. And I should put in the charges. +1, +1, +2, +3. And then the smallest would be chlorine -1. So if they give you an ion list in general, you can rank them with the same thought process that you would rank the atomic radii. The last example that they give me is a bunch of potassium, which it's kind of weird to see a potassium -1 ion. That's not stable. Not to say that it could never happen, it just wouldn't be stable. In this case, start with the neutral atom. Potassium +1 means that we're going to lose one electron. If we lose an electron, that +1 ion becomes smaller. Potassium -1 would mean that I gained an electron. If I gain an electron, in this case that's kind of weird and unstable, but it would cause more repulsion. I'd have to put another electron in that s orbital, and those two electrons would repel, causing a potassium -1 ion to be a little bit larger. So generally, look at what you've got, find them on the periodic table, and know the extremes. However, here's what we have to be careful of. Something called isoelectric ions. This was something that people kind of struggled with when we were reviewing for the AP test at the end of last year. This isn't a difficult concept, but it's definitely something you have to be careful of if you're ever asked to rank a list of ions. Check to see, number one, if they are isoelectric. Isoelectric means that you've got a group of ions that all have the same number of electrons. So for example, here's a real common group. Oxygen is element number 8. He normally has 8 electrons, but the oxygen -2 ion means we're going to gain 2 for a total of 10. Fluorine normally has 9, but the fluorine -1 ion gains 1 for 10. And so on. If I have the aluminum +3 ion, aluminum normally has 13 electrons, but a +3 ion loses 3. All of these ions have a total of 10 electrons. That's what it means to be isoelectric. Iso means the same. So we're referring to ions that all have the same amount of electrons. So be careful. If you have an isoelectric series, you have to treat them a little bit differently than you would otherwise. Here's what happens. They all have the same amount of electrons, but they do not have the same amount of protons. So as I go across, as I'm going from oxygen, number 8, and then all the way to something like aluminum, number 13, as you add more protons, you get a greater nuclear charge. I told you, become obsessed with this term. Nuclear charge refers to the amount of protons in the nucleus. How positive is the nucleus? So if we have something like oxygen -2, he's going to have 10 electrons, but he only has 8 protons. Now let's say I go all the way across to somebody like aluminum +3. 10 electrons, but 13 positive protons. Oh, interesting. A lot of people will get this wrong because, again, they'll say, whoa, you got like 13 protons? You got more stuff in this aluminum ion. There's more subatomic particles. That should make it bigger. Yes, aluminum has a bigger nucleus, but 99.9% of an atom's radius is the electron cloud. Somebody did a measurement one time, and it was like, the nucleus would be the size of a marble in the middle of a giant football stadium, where the rest of the stadium, that's the electron cloud. Okay, if I'm thinking about that then in terms of like the size of the atom, the radius, oh yeah, the nucleus is like barely making a difference. It's like a drop in the bucket. Yeah, there's a couple more protons and neutrons in the aluminum nucleus, but that really doesn't affect the radius of the atom. The radius is mainly affected by the electron cloud. And so here in aluminum, if I've got a stronger attraction between the nucleus and those existing 10 electrons, that's going to cause the atom to shrink a little bit. So when you have a greater nuclear charge, there's going to be, I should make a little arrow, that's going to cause greater attraction. And whenever you have more attraction between the electron cloud and the nucleus, you've got a smaller radius. So you have to be a little careful here. And again, other people will get this wrong because they'll look at the periodic table and they'll say, whoa, this is crazy. Aluminum, check out aluminum, he's in a higher energy level than oxygen. The electrons are distributed amongst more energy levels. Aluminum should be a larger radius. If we were talking atoms, yes, the aluminum atom is larger than the oxygen atom. But when you're talking isoelectric ions, you have to be very careful. As an ion, they really have the same amount of electrons. The second energy level is full. Tricky, isn't it? Because if you look at their position on the periodic table, you think that there's electrons in more energy levels. But you have to take into consideration the charge. Oxygen's gaining 2, aluminum's losing 3. And obviously this would pertain to like the fluorine and sodium and magnesium ions as well. When you have an isoelectric series, meaning check those ions and just see, like, are they all going to gain or lose electrons to the point where they have the same amount of electrons? Then you go, the smallest radius is the ion with the most protons. It's tricky. Now, we had a group of ions in this last example, this cesium, potassium, gallium, and all that stuff. These are not isoelectric. They do not gain or lose electrons to form ions with the same amount of electrons. So in that case, we can just rank them by their position on the periodic table. It would be the same as if I were looking at just the neutral atoms. But if you have something like this first set, strontium plus 2, rubidium plus 1, bromine minus 1, and selenium minus 2. When you have a group of ions and you're asked to rank them, so this time it's smallest radius to largest radius, double check for isoelectrics. So I always just kind of locate them on my periodic table first. Strontium, oh boy, rubidium, bromine, and selenium. And you'll kind of notice this too, that they like all go in a row. Now, in this periodic table, they obviously left out the noble gas because all of these ions are gaining or losing electrons to look like the nearest noble gas, which is krypton, number 36. So for example, selenium is number 34. Selenium minus 2 means he's gaining 2 electrons for a total of 36. Strontium is normally number 38. As a plus 2 ion, he's going to lose 2 for a total of 36. This is an isoelectric series. I'm going to make that a note. Isoelectric. It's something that people miss all the time. But again, notice like if they're all in a row, that might set off a little red flag. So now I'm going to rank these smallest to largest. The smallest will be the ion with the most protons. They all have the same amount of electrons. And again, the electron cloud is what makes up most of the radius. They all have the same. But strontium has the most protons. So there's going to be the greatest attractive force coming from the nucleus. So strontium is going to be the smallest. The strontium 2 plus 2 is going to be the smallest. Next would come rubidium plus 1. And then bromine minus 1. And the smallest will be that selenium minus 2, or 2 minus. He's got the least amount of protons, so the least nuclear attraction. But again, now check out this next list. Here's another series. Lithium. Sodium. Oh yeah. Potassium. Rubidium. And cesium is not on this little periodic table, but if he were, he'd be down at the bottom. This is not isoelectric. Yeah, they all form plus 1 ions, but they do not have the same amount of electrons, which means their electron clouds are going to have very different sizes. So now this one I can just rank by normal periodic trends, piece of cake. Smallest to largest, lithium plus 1 would be the smallest. Everybody's losing 1 electron. Then would be sodium, potassium. Hey, what do you know? They're in the right order. Rubidium and cesium. Cool. So watch for series of ions. When they ask you to rank a bunch of ions in order of increasing radius or something like that, check to see if they're isoelectric, which means that they'd be kind of like in a row. They'd be increasing in atomic number. Then you got to be careful. The smallest ion will be the one with the most protons. If it's not isoelectric, you can just rank them by their normal periodic trends.